In this lecture, we shall do some problems on hydrostatics, that is on pressure and buoyant force. And this additional notation at right top corner, this C is standing for competitive examinations, which means that we shall choose the problems specifically from various competitive examination papers. So let us move on to the second problem in this lecture, which is based on the concept of buoyancy. And this one is telling a hemispherical portion of radius r is removed from the bottom of a cylinder of radius r. The volume of the remaining cylinder is V and its mass is m. It is suspended by a string in a liquid of density ρ, where it stays vertical. The upper surface of the cylinder is at a depth h below the liquid surface. Calculate the force on the bottom of the cylinder by the liquid. So let us construct a figure to understand the situation of the problem. This is the body that is immersed in the liquid. Originally it was a cylinder, but as you can see from the bottom, a hemispherical part of the same radius as the cylinder has been cut out. And for this cylindrical element, the volume is capital V and mass is m. It is suspended by a string from the ceiling, say, and immersed inside a liquid, as I am showing in the figure. So they have given further the density of this liquid is ρ, and the top surface of this cylindrical immersed body is at a depth h below the free surface of the liquid, and as I have already said, the radius of either the cylinder or the hemispherical part removed from it, that radius is r, and therefore the diameter of the cylinder is coming out to be twice r. Now we have to find out the force on the bottom of the cylinder. You are aware that if I could know the depth of the bottom, in such case I could find the pressure acting on this body at this point. But I am not given this height of the cylinder, and therefore I don't know the depth of this point. Not only that, this hemispherical portion cut out has left behind a curved bottom that has got variable depth below the free surface, as well as, since the force of pressure always acts normal to any point along this curve, it is not a simple job to add up all those forces vectorially. So let us go for some alternative approach and see how we can find out the force of pressure acting on the bottom. As a first step, we identify the forces acting on this immersed cylinder. One of them is the downward force of pressure exerted by the liquid on the top surface of this cylinder. I'll be calling it as FD, D for down, in my figure to keep it clean, but while writing I'll be using more elaborate symbols for that. This is the downward force of pressure given by the liquid on the top surface of the cylinder. And similarly, on the curved bottom surface of the cylindrical body, there is a force of pressure acting upward. Let me call it FU, U for upward force of pressure. In addition to these pressure forces, there is a force of gravity acting vertically downwards. Since mass was given to be capital M, gravity force is mg, and a force of tension exerted by the string of suspension along the length of the string. That I'll call it as the force of T. So if I could take my upward direction as plus y direction, I might write down the equation of equilibrium for the cylindrical body. You can see here already in the horizontal direction, the forces of pressure are acting radially inwards all around this curved lateral surface so that they cancel each other by symmetry. So there is no need for writing down the equation for horizontal equilibrium. That gives us no useful result. Writing down the equation for equilibrium in the y direction, sigma Fy, well, I'm taking upward to be positive. So first I write down the force of pressure upwards, that is this Fu. I call it the force of pressure in the upward direction. It's positive because it's upward. And there is a force of pressure acting downwards at the top surface. So that's minus the force of pressure acting downwards now. In addition to these two pressure forces, a gravity force acting downwards, therefore minus mg, and a force of tension acting upwards, that is plus T, this net force in y direction must be 0 because the cylinder in immersed condition doesn't have any vertical motion or acceleration. Now this was application of Newton's second law to write equation of motion. We don't need to pursue it any further, and we should recognize by this step now that, let me highlight this quantity. This quantity, the force of pressure upwards minus the force of pressure downwards, this net force upward is referred to as the force of buoyancy exerted on this immersed body by the liquid. We have learned the force of buoyancy is the vector sum of all the pressure forces acting on the body exerted by the liquid, and in this case horizontal forces cancel each other out and the vertical force upward is greater than the downward force, and net force acts upward, and that is called the force of buoyancy. So I shall pick up from here, take out this part, apply Archimedes' principle and find out the force of pressure acting upward. So let me write it. Well, I could just show another figure by the side. If I would have drawn the free body diagram of this immersed body, I could also show by these three forces only. Just as an elaboration, you understand, this is the force of gravity acting downwards mg, this is the force of tension acting upwards, and the net resultant of the pressure forces, that is F upwards and F downwards, their vector sum is given by this tiny upward arrow. This is the force of buoyancy. This you must recognize all the time, that in my previous figure, whatever force of pressure I have shown, their net sum is nothing but the force of buoyancy acting upward. So this figure and this figure are completely equivalent. Once you recognize that, let me write separately that the force of buoyancy acting on the immersed cylinder is equal to the force of pressure acting upwards minus the force of pressure acting downwards. And therefore, we are supposed to find out the force of pressure acting upwards at the bottom of the cylinder, right? So this is coming out to be the force of buoyancy plus the force of pressure acting downwards at the top surface of the cylinder, this one, Fd. So at this moment, let us recall Archimedes' principle, which says that the buoyant force acting on an immersed body has the same magnitude as the force of gravity acting on the displaced liquid. Since volume of this cylindrical part has been mentioned to be capital V, this V is also the volume of the displaced liquid. And since density of the liquid is given to be rho, we understand this buoyant force acting on this body is given by the displaced volume of liquid V into density of liquid rho into the free fall acceleration.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.